Hi, I'm making this video to help you reduce fractions using prime factorization. Okay, so let's say you have the fraction 36 over 108. Like I said, there's a few different ways to reduce fractions, but we're going to use prime factorization. It's a very powerful way because we're not just kind of doing it by eye, and it's very complete. We find every single factor they have in common, and we're going to cancel them. So we'll see how this works. First, we prime factor each number, and sometimes breaking down each number is not so bad. So when we prime factor, the numbers get smaller really fast. So this is a little easier than other traditional methods sometimes. So 36, we can say that's 3 times 12. And then the 3 is now prime. So I can't break the 3 into anything other than 3 in itself. So that's this branch has gone as far as it's gonna go. Now with 12, I can say that's 3 times 4. Now this branch as far as it's gonna go, but then at 4, I can say it's 2 times 2. So we just keep breaking each number in this tree down until there's no other number except for 1 in itself that it can break into. It can factor into, So then we say the prime factorization of 36, I'm gonna write it above the fraction here, is where every branch stops. So here's the stop, and imagine water rolling down. So it would roll here, so that's one number. So it would roll here, that's another number. It would roll all the way to the bottom. It would get to the 4, right? But it would roll past the 4, and it would start pulling up at the bottom right here and right here. So all these 4 numbers, if we multiply them all together, they make 36, but they are the prime numbers that the smallest. It's kind of, I feel like it's like the elements of that number. Like if you break down, if you take like a substance and you break it down to smaller, what made it up, what it made up, if we take like cookies and you're like, okay, well, what was it made of? Okay, well, it was made of eggs, and it was made of flour, and it was made of sugar. And we break it down further. Well, what was the flour made out of? Okay, well, that was made out of, carbon and blah, blah, blah. You get and you break that little molecule down and you break it down to its basic building blocks. That's like what a prime factorization is, I think. I feel like it's like the DNA of a number, because no matter how you break it down, those are the same. You're going to get the same numbers whenever you prime factor something. So it's 2 times 2 times 3 times 3. And I think that's some confusion for students. They think, well, they notice how, the way I did this, 36, I factored it into 3 and 12. They're like, well, what if I factored that differently? What if I said 36, that's 6 times 6? Wouldn't I get a different set of numbers at the end? And you don't. And that's the thing about prime factorization, is that you never, when you factor something normally, like if I just factor it once, like, oh, tell me 2 numbers that multiplies to 36, then you could say 3 times 12 is 36. And somebody else could have a different, but also correct answer, 6 times 6 is 36, right? But if they both have factored and them down all the way, so it's like a prime factorization, then no matter which manner in which they did it, they're going to get the same prime factorization if they both did it correctly. So like, watch. So I did the 3 times 12 first. I factored 36 into 3 times 12. And now I'm going to do it again, but factor by 6 and 6. So it's 2 times 3. And then the other 6 will be 2 times 3. And notice I'm going to get the same. I get 2 2s and 2 3s. So it's going to be the same exact prime factorization as before. And so no matter how you break it down, that DNA, the number, is still going to be the same. That prime factorization is going to be the same. Okay. And now let's focus on the 108. So 108, I can say that is 9 times 12. And that's 3 times 3, and that's 3 times 4. And 4 is 2 times 2. So, and we could just double check, maybe we made a mistake somewhere in there. If we multiply all these prime factors back out, we should get back to the original number. So, and sometimes if I'm like, if I forget, I'm like, is 9 times 12, is that 108? Well, I can double check that quickly. That's 18 and 10, 108, right? But if I could also double check it by multiplying those numbers all back out in kind of a different manner, and then that would double check that as well. But let's look. So it's 3. Okay, so these are all the prime factors of 108 at every branch, the end of every branch. So that's 3 3s and 2 2s. So 1, 2, and 3 3s, 3, 3, and 3. Okay, so now I prime factored both of the numbers in the numerator and denominator. And now what happens next is I cancel any common factor to the numerator and denominator. This is the equivalent division is opposite of multiplication, like undoing the multiplication. And division, and when I cancel a factor, like, okay, let's not multiply this number by 2 anymore. It's the same as dividing, because if doing the opposite of multiplying by 2, it was either dividing by 2 or canceling your multiplication by 2. And when I cancel, I'm like, I decide not to multiply by 2, then it's like dividing by 2, the same thing. So and since it's the idea is we're kind of dividing by 2, when we cancel a factor in the numerator, I'm actually dividing the top number and denominator by 2. I have to be careful here. If there's any addition, I could not cancel. You could only cancel when you have common factors, not add-ins, or not if you have an expression like 2 plus 4 in the numerator, you would have to factor out the 2 first and write an expression of factors in the numerator, and because these are add-ins, and you can't have you couldn't do this, because these are numbers being added together. We're not canceling numbers being added together. We can only cancel a series of numbers that are being multiplied together. Factors are the numbers being multiplied together. Okay, so that's a big issue here. But okay, so I see, and then 1, 2 in the numerator for every 1, 2 in the denominator. Okay, so that pair got canceled, and then I have a second pair of 2s that also got canceled. Then I get a second pair of 3s and a second pair of 3s. Ooh, I'm glad this happened, but now we're left with no numbers in the numerator, but that can never happen. We can always put a 1 in the numerator. And notice how that wouldn't change the fact that there was 36 in the numerator. If I multiply 36 by 1, it's still going to be 36. So multiplying by extra 1 and leaving, because you can't have, it's just kind of like a placeholder. You can't have nothing in the numerator. So it's 1 over 3 is what 36 over 108. It goes to 103. I'm sorry, it reduces to 1/3. That's my first problem. We're all done with that one. Okay. One thing I did want to mention to you, sometimes there might be really hard problems, and this whole idea and concept of prime factorization and using it to reduce a number, let me do it. Sometimes we don't have to do the whole process to really find out a lot of information about a number, because sometimes using this idea, we can just start the process a little bit, and then it'll give us some valuable information. So let's say that I have the number 24 over 55. Well, I can quickly factor 55 real fast. I know 55 is 5 times by 11, right? And those are kind of both big prime factors, and that's a prime factorization. It doesn't break down any further. So one thing, if I'm trying to reduce a fraction, or if I'm just trying to identify whether it could be reduced or not, what I can do is I can take a number, either top number or the bottom number, and just look at that number only. So just look at, I factor 55 only. And the key here is the only way that this fraction is going to be able to be reduced is if 5 goes into 24 equally, or the 11 goes into 24 equally, because like we saw before, if the only numbers that can cancel are prime factors that are common to both top and bottom. And so that's the only things that are going to cancel here. So because the prime factorization of 55 is 11 and 5, the only way that this fraction is be is if we can write 24 as 5 times something, then we could cancel those 5s, right? So, and we know that that's not possible. So that this is a real quick way that I know that if 5 doesn't go into 24 and 11 doesn't go into 24. So I know that this fraction cannot be canceled either way, because anyway. So sometimes that can be a really fast way to immediately see that 24 and 55 do not have any common factors. Otherwise, you're going to be kind of sitting here for a long time and like thinking, oh, well, does 2 go into 24 and 55? Does 3 go into 24 and 55? And does 3, does 4, does 7, does, you're going to be sitting here for a long time. See, when I prime factor the 55, I quickly see the only 2 numbers I have to check that divide into 24 are 5 and 11. And once I'm done checking that 5 and 11 don't go into 24, I know that this is completely reduced. Okay, so that's what's so valuable about this let's reduce with prime factorization method. All right, I hope you really found this valuable, and like the larger the numbers, the even better that this method works. Like if you have like 555 over 24 and you're like, can that be reduced? Like then you can take the smaller number and be like, okay, well, I can prime factor 24, and if none of the prime factors go into 55, then I know this number is completely reduced. So it can be very, it can very simplify this process a lot. All right, have a great day. Bye.